High above us in the constellation Corona Borealis shines a star with a secret. This constellation, often overlooked, holds within it a star that has intrigued astronomers for generations. It appears unassuming most of the time, a faint glimmer in the cosmic tapestry. To the naked eye, it might seem like just another star, blending into the vast expanse of the universe. But this star, known as T Corona Borealis, is far from ordinary. Through the lens of a powerful telescope, its true nature begins to reveal itself. It's a celestial chameleon, capable of transforming from an inconspicuous point of light into a blazing beacon in our night sky. This transformation is nothing short of spectacular, capturing the imagination of those who witness it. T Corona Borealis belongs to a rare class of stars called recurrent novae. These stars are unique in their ability to undergo multiple explosive events over their lifetimes. These stellar objects don't just explode once and fade away. Instead, they have the remarkable ability to erupt repeatedly, each time returning to a dim state before the next outburst. Instead, they undergo periodic eruptions, dramatic outbursts of energy that make them shine thousands of times brighter than usual. These eruptions are a testament to the dynamic and ever-changing nature of our universe. These eruptions are not random. They follow a pattern, a celestial clock that has fascinated astronomers for centuries. By studying these patterns, scientists hope to unlock the secrets of stellar evolution and the life cycles of stars. T Corona Borealis is a binary star system, a cosmic dance between two stars locked in a gravitational embrace. This intricate dance is a key factor in the star's dramatic behavior. One star is a red giant, a star in the later stages of its life, swollen and cool. This aging giant has expanded to many times its original size, its outer layers drifting away into space. The other is a white dwarf, the dense, hot remnant of a star like our Sun. This compact star is incredibly dense, with a mass comparable to the Sun, but packed into a volume similar to Earth. It's this unlikely pairing that sets the stage for the spectacular explosions that define T Corona Borealis. The interaction between the red giant and the white dwarf creates a cycle of mass transfer and explosive outbursts, a cosmic phenomenon that continues to captivate and inspire. The secret to T Corona Borealis's eruptions lies in the unique and intricate relationship between its two stars, a red giant and a white dwarf, locked in a cosmic dance. The red giant, with its vast size and relatively loose outer layers, has a tenuous grip on its outer atmosphere. This outer layer is rich in hydrogen, the most abundant element in the universe. These hydrogen-rich layers are drawn away by the intense gravitational pull of the white dwarf companion, which is much smaller but incredibly dense. This hydrogen doesn't just fall directly onto the white dwarf, instead it spirals inward, forming a swirling disk of gas known as an accretion disk. This disk is a dynamic and turbulent region. Over time, as more and more hydrogen is pulled in, this disk grows denser and hotter, accumulating vast amounts of potential energy. The pressure and temperature at the bottom of this disk become so extreme that they ignite nuclear fusion, the same powerful process that fuels our Sun and other stars in the universe. But this fusion is not a gentle, steady burn like in the core of a star. Instead, it is a sudden, runaway explosion. This runaway explosion results in a sudden release of energy that blows the accumulated material off the white dwarf's surface in a dramatic fashion. This explosion is what we observe as a nova, a brilliant outburst of light that can temporarily outshine all the other stars in its vicinity, making it visible even from great distances. Unlike supernovae, which mark the cataclysmic death of a star, novae are not final acts. They are more like dramatic episodes in the ongoing life of the binary system. The white dwarf survives the explosion, and the cycle of accumulation and eruption begins anew, continuing this celestial pattern. Hydrogen from the red giant continues to accumulate on the white dwarf, setting the stage for another spectacular eruption, ensuring that the cycle of recurrent novae continues. The year was 1946, a time of great change and hope. World War II had just ended, and people were looking towards a brighter future, filled with optimism and a sense of renewal. On February 12th, T Corona Borealis, usually a faint star barely visible to the naked eye, suddenly flared to life, capturing the imagination of astronomers and the general public alike. It became so bright that it was easily visible even from light-polluted cities, a rare and awe-inspiring sight that brought people together in shared wonder. This wasn't the first time T Corona Borealis had put on such a show. Its previous outburst had been recorded in the annals of astronomical history. Astronomers had recorded a similar outburst in 1866, marking the star as a recurrent nova, a celestial phenomenon that repeats over time. But the 1946 eruption was special, occurring at a pivotal moment in the history of astronomy. It occurred when astronomy was entering a new era, with more powerful telescopes and instruments capable of studying the event in unprecedented detail, allowing scientists to gather more data than ever before. Astronomers around the world turned their telescopes towards the blazing star, eager to unravel its secrets and understand the mechanisms behind such dramatic stellar events. They meticulously recorded its changing brightness, its color, and every subtle variation in its appearance. And its spectrum, the unique fingerprint of light that reveals the chemical composition and physical conditions of distant objects, providing invaluable information about the star's properties. The 1946 eruption of T Corona Borealis provided a wealth of data, offering crucial insights into the physics of novae and the dynamics of binary star systems, enriching our understanding of the universe. It solidified our understanding of these celestial phenomena and laid the groundwork for future research, inspiring generations of astronomers to continue exploring the mysteries of the cosmos. Based on its past behavior, T Corona Borealis was expected to erupt again sometime in the late 20th century. Astronomers eagerly awaited this event, their telescopes trained on the star, ready to capture every detail of the unfolding spectacle. But the decades passed, and T Corona Borealis remained stubbornly quiet. Now, as we stand at the cusp of 2025, the star's silence has become a tantalizing mystery. Why hasn't T Corona Borealis erupted as expected? Have we misjudged its cycle? Or are there other factors at play hidden from our view? Some theories suggest that the transfer of material from the red giant to the white dwarf might be episodic, with periods of intense flow followed by lulls. Others propose that the white dwarf's magnetic field, often overlooked in nova models, might be playing a significant role in regulating the accretion process. This delay, while unexpected, has only heightened the anticipation and excitement surrounding T Corona Borealis. It's a reminder that the universe is full of surprises, and even the best-studied objects can still hold secrets waiting to be uncovered.